Hello, in this video I want to introduce a very important result for Markov chains called the Chapman-Kolmogorov relationship. This sounds horribly complicated, but I hope that by the end of this video I will have convinced you that it really isn't, and that you will be able to explain what the Chapman-Kolmogorov relation states, and that you will be able to calculate n-step transition probability matrices if I give you a one-step transition probability matrix of a Markov chain. Before we get on to those, then, let's briefly remind ourselves what a Markov chain is. In our previous video on Markov chains, we stated that a time series of random variables is Markovian if it has the following properties. In other words, a time series of random variables is Markovian if the future values of the random variable depend only on the value the random variable has at the present time. The random variable must be independent. The value of the random variable in the future must be independent of the values that it had in the past. We showed that when the time series of random variables have this property, their behavior can be represented by using a transition graph like the one shown here. The possible values the random variable can have are shown in circles, so in this example our random variables can have the values a, b, or c. Instead of talking about the values the random variable can have, though, we state that the circles represent the states the system can be in. The circles that represent these states are then connected by arrows, and above these arrows, numbers between 0 and 1 appear that represent the probability of moving between the two connected states in a single time step. So in this example, the probability of moving from state C to state A in a single time step is equal to 0.8. Alternatively, we might state that the probability that the random variable has a value of C followed by a value of A is equal to 0.8. In the previous video, we introduced one final representation of the Markov chain, the transition probability matrix. We said that the rows of this matrix represent the initial state the system is in, and that the columns represent the state the system moves into during the step. We said that you can find the AB element of this transition matrix by reading the probability of moving from state A to state B in one step from the transition graph as shown here. This is all well and good. In this video we want to answer one further question about Markov chains. We now know how to obtain the probability of T2 being equal to A, B, or C if T1 equals A. We can read this information off either the transition graph or from the one-step transition probability matrix. What we would like now is to determine what the conditional probabilities that T3 takes on these three different values. In other words, we would like to know whether or not we can make predictions about the state of the system after two or more time steps rather than after a single step. Pleasingly, in this video, I am going to show that we can also extract this information from the one-step transition probability matrix. To see how, let's first consider the probability that the following happens in the future. We start with T1 equals A, we then move to state C so that T2 equals C, and we then move from state to state B so that T3 equals B. We know that we can get the probability of a single step from A to C from the transition matrix. The symbol for this quantity is shown above here. What is more, we know that once we arrive in state C, that is to say once T2 equals C, the system immediately forgets about the fact that T1 was equal to A. The process is after all Markovian, and the state the system was in the past do not affect the probabilities of being in the various states in the future. Once we have moved from T1 equals A to T2 equals C, T2 equals C becomes the present state of the system. As a consequence of this, we can also get the probability of the second transition, shown here, T2 equals C to T3 equals B, from the one-step transition probability matrix. It gets better still though. Because of the Markov property, the event of moving from state t1 equals a to t2 equals c is independent of moving from t2 equals c to t3 equals b. Remember that the Markov property ensures that the system immediately forgets everything that happened in the past as soon as it has happened. Thus, two adjacent transitions are completely independent of each other. The only thing that affects the value of t3 is the value of t2. This is what the Markov property ensures. Now remember that we can obtain the probability that two independent events occur by multiplying the two individual probabilities together. Consequently, for this particular problem, we can calculate the probability that the system will move from t1 equals a to t2 equals c, and then on to t3 equals b, by multiplying the conditional probability that t2 equals c given t1 equals a by the conditional probability that t3 equals b given t2 equals c. Let's now suppose that we want to calculate the probability that we move from state A to state B over 2 steps. As shown in the figure, there are 3 ways that this might happen. We can go from state A to state C and then on to B. We can go from state A to state B and then remain in B, or we can remain in A for 1 step and then transfer to B. We can use the logic introduced on the previous slide to calculate the probabilities of each of these individual pairs of events. The probabilities of each of these pathways are shown here. Now the next thing to realize is that each of these pathways is mutually exclusive, as the random variable t2 can only have one value. It cannot have 2 values simultaneously. We can thus obtain the total probability of moving from state A to state B over the course of 2 steps by adding together the probabilities of each of the paths as shown. If we have 3 states, we can write out everything explicitly. When we have more than 3 states, however, this writing out of everything explicitly gets rather annoying. We thus use series notation instead, as shown here. The sum here runs over all the possible values that the random variable t2 can take. Now those of you who are really on the ball might have noticed that this sum of products is nothing more than the definition of the matrix product. Furthermore, because our Markov chain is homogeneous, the first matrix and the second matrix here are identical. We are thus taking powers of the matrix. We can thus get the 2-step transition probability matrix from the 1-step transition probability matrix by multiplying the 1-step transition probability matrix by itself. If we then want the 3-step transition probability matrix, we take this 2-step transition probability matrix and multiply it by the 1-step transition probability matrix much more. In general, we thus write that the n plus m step transition probability matrix is equal to the product of the n-step transition probability matrix and the m-step transition probability matrix. This result is known as the Chapman-Kolmogorov relation, and it is extremely useful. In general, it means that we can calculate the n-step transition probability matrix by taking powers of the matrix, as shown here. Here's the 3-step transition probability matrix, which is just the 3rd power of the 1-step transition probability matrix. The 4-step transition probability matrix, which is just the 4th power of the 1-step transition probability matrix. The 10-step transition probability matrix. The 20-step transition probability matrix. The 100-step transition probability matrix. To summarize then, we have learned what the Chapman-Kolmogorov relation is, and we have learned how, once we have the 1-step transition probability matrices, we can calculate the 2-step, 3-step, 4-step, or any number of step transition probability matrices. We simply take matrix powers of the 1-step transition probability matrix. I hope you've understood all this from this video, but if not, watch it again and see if you can get it on the second time through. Thank you for your attention.